Alright, so today I'm going to be explaining another important article for domain adaptation, and we are using the paradigm of adversarial discriminative methods. This adversarial training that you're familiar with in GANs. I've explained GAN's paper in a playlist for generative AI. So that is the prerequisite for this article. So I'm going to be explaining this article in 2017. Adversarial learning methods are a promising approach to training robust deep networks and can generate complex samples across diverse domains. They also can improve recognition despite the presence of domain shift or dataset bias. Several adversarial approaches to unsupervised domain adaptation have recently been introduced, which reduce the difference between the training and test domain distributions and thus improve generalization performance. Prior generative approaches show compelling visualizations, but are not optimal on discriminative tasks and can be limited to smaller shifts. Prior discriminative approaches could handle large domain shifts, but imposed tight weights on the model and did not exploit the GAN-based loss. So this is an overview of adversarial domain adaptation methods and their various properties. Viewing methods under a unified framework enables us to easily propose a new adaptation method, adversarial or discriminative domain adaptation. So we have weight sharing and we have adversarial loss. So it's a combination of the base model and the other. So it's a framework. I will show you that this is a framework. Each article, for example, weight sharing, this article uses unshared. This article for base model, it uses discriminative rather than generative. So we first outline a novel generalized framework for adversarial adaptation, which subsumes recent state-of-the-art approaches as special cases. And we use this generalized view to better relate the prior approaches. We propose a previously unexplored instance of our general framework, which combines discriminative modeling, untied weight sharing, and a GAN loss, which we call adversarial or discriminative domain adaptation. So it first learns a discriminative representation using the labels in the source domain, and then a separate encoding that maps the target data to the same space using an asymmetric mapping learned through a domain adversarial loss. For example, your source domain could be these street view images and your target is just the MNIST. So this is the architecture. So each paper, as I said, for example, this component of this framework could be implemented differently in each paper. So that's why this is a good framework to think about. Because all of these papers, 100 papers, have source input, target mapping. They implement using different adversarial objective. They have source mapping, target mapping. It could be generative or discriminative. And this is a technical thing. It is weight tied or untied. So we present a general framework for adversarial unsupervised, and this is a general framework. In unsupervised adaptation, we assume access to source images and Of course, we have also source-free. Some articles work on source-free. And because of the privacy issues, sometimes we don't have the companies in enterprise scale, the companies don't provide the source domain. So you just have a black box of their input output. And so you try to learn, still you can learn, but you don't have access to the data, but you have access to the input and an output. But that's a different story, source-free. But in unsupervised adaptation, we assume still access to source images, X sub S and Y sub S, drawn from source distribution, no problem for privacy. We are not interested in privacy in this article, so it's a standard approach. Our goal is to learn a target representation, M sub T, and a classifier C sub T that can correctly classify target images into one of K categories at test time, despite the lack of domain annotations. Since direct supervised learning on the target is not possible, domain adaptation instead learns a source representation mapping along with a source classifier, and then learns to adapt that model for use in target domain. In adversarial adaptive methods, the main goal is to regularize the learning of the source and target mappings so as to minimize the distance between the empirical source and target mapping distributions. If this is the case, then the source classification can be directly applied to the target representation. That's why we don't distinguish them. We say it's C, it's a classifier. Now we are now able to describe our full general framework view of adversarial adaptation approaches. We know that all approaches minimize source and target representation distances through alternating minimization between two functions. First, a domain, D, is discriminator. First, a discriminator, which classifies whether a data point is drawn from source or target. Thus, D is optimized according to standard supervised laws. Then the source and target mappings are optimized according to constrained adversarial objective, whose particular instantiation may vary across methods. Thus, we can derive a generic formulation for domain adversarial techniques below. In the next sections, we demonstrate the value of our framework by positioning recent domain adversarial approaches within our framework. We describe the potential mapping structure, mapping optimization constraint choices, and finally choices of adversarial mapping laws. Because unsupervised domain adaptation generally considers target discriminative tasks such as classification, previous adaptation methods have generally relied on adapting discriminative models between domains. Once the mapping parametrization is determined for the source, we must decide how to parameterize the target mapping. In general, the target mapping almost always matches the source in terms of specific functional layer, but different methods have proposed various regularization techniques. All methods initialize the target mapping parameters with the source, but different methods choose different constraints between the source and target mappings. The goal is to make sure that the target mapping is set so as to minimize the distance between the source and target domains under their respective mappings, while crucially also maintaining a target mapping that is category discriminative. Consider layered representation, where each layer parameters are denoted as m sub s and m sub t for a set of layers. Then the space of constraint explored in the literature can be described through layer-wise equality constraint. So each individual layer can be constrained independently. And a very common form of constraint is source and target layer-wise equality. For each layer, they should be equal. It is also common to leave layers unconstrained. These equality constraints can easily be imposed within a convolutional network framework through weight sharing. For many prior adversarial adaptation methods, all layers are constrained, thus enforcing exact source and target mapping consistency. Learning a symmetric transformation reduces the number of parameters in the model and ensures that the mapping used for the target is discriminative, at least when applied to the source domain. However, this may make the optimization poorly conditioned, since the same network must handle images from two separate domains. An alternative approach is instead to learn an asymmetric transformation with only a subset of the layers constrained, thus enforcing partial alignment. And this author, he showed that partially shared weights can lead to effective adaptation in both supervised and unsupervised settings. As a result, some recent methods have favored untying. This is a very technical thing, untying weights between the two domains, allowing models to learn parameters for each domain individually. So once we have decided on a parameterization of M sub t, we employ an adversarial loss to learn the actual mapping. There are various different possible choices of adversarial loss functions, each of which have their own unique use cases. All adversarial losses train the adversarial discriminative using a standard classification loss. So the gradient reversal of that paper that I explained optimizes the mapping to maximize this discriminative loss directly. This optimization corresponds to true minimax objective for generative adversarial net. However, this approach can be problematic. This is very important. Since early on during training, the discriminator converges quickly, causing the gradient to vanish. So that's why that article is not very, very successful. That article that I explained was not good. So this article is an improvement because you can adjust the frequency of training. Some of them are fast, some of them slow, like fast, slow dynamical systems. So when training GANs rather than directly using the minimax loss, it is typical to train generator with the standard loss function with inverted labels. This splits the optimization into two independent objectives, one for generator and one for discriminator. And this adversarial loss remains unchanged, but adversarial of M becomes this minus expectation of log of your discriminator of M sub t. So this objective had to have the same fixed point properties as minimax, but provide stronger gradients to the target mapping. And the GAN loss is a standard choice in the setting where generator is attempting to mimic another unchanging distribution. However, in the setting where both distributions are changing, this objective will lead to oscillation. Still problem. When the mapping converges to its optimum, the discriminator can simply flip the sign of prediction and response. And so these researchers instead proposed the domain confusion objective, under which the mapping is trained using a cross-entropy loss function against a uniform distribution. This loss ensures that the adversarial discriminator views the two domains identically. So you see the different base model weight sharing and adversarial loss. Next, we choose to allow independent source and target mappings by untying the weights. This is a more flexible learning paradigm as it allows more domain-specific features to be learned. We have domain, let's say domain invariant features, and domain-specific features. In these articles, when we say domain invariant, it means that is some features that, for example, your backbone, it is shared among different paths in your model. But when it is domain specific, it means although some of them are shared, but some of the features are unique to that source I, source 1, source 2, are unique to that one. So if this is your feature space, I can say, for example, 80% is domain invariant, so it is shared. But the rest of that, which is domain specific, depends on the domain. For domain, for example, I, for source domain I, for example, we have a different thing. For J, we have a different thing, different values. Our proposed method just corresponds to the following unconstrained optimization. So this is a classification loss. As I said, it could be anything, C1, C2, all of them are equal. But we have also the adversarial loss. And you see, first we do pre-training, then adversarial adaptation to see if it is coming from source or target. And finally, you just test it, your classifier, and that is the domain adaptation. So as I said, source images could be street view images, but the target is just a standard MNIST. And you see if it is coming from the source or from the target. So if you go from source to the target, you have a different source, different target. You have different accuracies. So because we have three different data sets, different sources, you have different combination from this one to this one, this one to this one, this one, source to this target.